we are only considering this symbol, that is less than or equal. Also here there will be n number of inequality constant. Okay. So the first step is always to form the Lagrangian, okay, because we want to convert this constraint of the dimension problem into the unconstrained one. So what will be our Lagrangian? It will be the L, and it will be the function of x, lambda, and mu. X is the decision variables that we will get from our main objective function, and lambda is the Lagrange multipliers, that is a penalty term, comes from the equality constraint, and mu is the slack variable, right? This is the slack variable. It will be the compensation for the inequality constraint. That's why we can write the Lagrangian like this way: f of x plus
says that we have to do the partial derivative of this Lagrangian with respect to the first variable, that is the x. Okay. If we do it, okay, then we have to equate that thing with 0. Okay. That will be the first necessary condition. The second will be the partial derivative of the L with respect to the second variable, that is the lambda. And if we do this, we will get ultimately the equality constant itself, that is the omega of x equals to 0. So how actually we are getting this kind of thing? Can you understand? Because from the previous type as well, you can see that whenever we are doing the partial derivative of the Lagrangian with respect to the lambda, then we get the g of x actually, right? We get directly the g of x because other terms cancel out. So we get directly g of x. That's why here we can write the second condition directly. But obviously this second condition is nothing but the partial derivative of L with respect to the lambda. Okay, then we will get only this thing because here this will be cancelled out, this will be cancelled out. Okay, so lambda will be 1, there will be only omega of x that will be equated with 0. Okay, that is the truth. Then the third condition is that we have to do the partial derivative of this Lagrangian with respect to the mu, the third variable, right? And at that time, look, this will be cancelled out, this will be cancelled out, only there will be g of x, right? And we can equate it with 0 because this is an inequality constant. Okay, that's why you have to maintain this symbol that is less than or equals to 0. Okay, so this is the condition number 3. So we discussed the first 3 conditions in the last class. Now we will start from the condition number 4. Okay, so what is condition number 4? This is called the complementary slackness condition. Okay, because here we have the mu. Mu is the slack variable. Okay, what is the meaning of slack? Slack means the loose. Okay, that means not tight or the flexibility. That means this variable mu will give some kind of flexibility in our solution. That's why this mu is the slack variable. Okay. How? That means we will now see. Okay. Let's say we have one inequality constant like this, x1 plus x2. That should be less than or equal to 3. Okay. Let's say this is our inequality constant. Okay. Now we will convert this inequality constant into the equality one. Okay. How? Using this new variable, that is the slack variable. Okay. Look, we will simply add this mu. Okay. With this x1 plus x2, then we will write that is equal to 3. Okay. Now, what is the value of mu? Okay. Let's think about different sets of solution for x1 and x2. Let's say for case number 1, we are getting x1 as 3 and x2 as minus 1. Okay. At that time, what will be the value of x1 plus x2? It will be 3 minus 1. Okay. That is equal to 2. Is it less than 3? Yes, right? It is less than or equal to 3. Okay. So how now? What will be the value of this mu now? To equate it with 0 for this case, mu should be plus 1. Okay, mu should be plus 1. That was understood. Okay. This is, let's say in the first case we are getting x1 equals to 3, x2 equals to minus 1. So after applying this condition x1 plus x2, we are getting 2. That is obviously less than 3, right? If this is the case, and using this formulation we are converting the inequality constant into the equality one. So what will be the value of mu for this case? It will be plus 1, right? Actually it will be 1, right? Because the plus sign is already here. Okay, now think about another case. Let's say the x1 is 3, okay, and x2 is, let's say, 0. So what will be the x1 plus x2? It will be 3 plus 0, that is equal to 0, right? So is it satisfying this condition, less than or equal to 3? Right, because there is also equal sign here, right? So it is actually equal to, it is fulfilling the condition. Now what will be the value of mu? Now 0, right? Okay. So look, in the first condition, whenever the x1 plus x2 is less than 3, mu takes some positive value, right? Either 1 or 2 depending on the value of x1 and x2. But whenever x1 and x2, the addition of x1 and x2 are exactly equal to 3, at that time mu will be 0. Okay. Now think about another case. Let's say our x1 is 3 and x2 is plus 1. Okay. So that will be 3 plus 1 equals to 4. That is obviously greater than this 3. So now this condition is violated, right? Now what will be the value of mu? Mu should be minus 1 to follow this equation, right? But actually this is the infeasible solution. So we do not need to assign any value for mu. Okay? Because this solution set will be discarded automatically because this is not satisfying this equation. Whether you set it to minus 1 or not, it will follow this equation, but the main equation that you are actually considering, that things already violated, right? That's why this set is infeasible. right? So there is no mu here. Okay, so there is no meaning of the mu here. So
that means mu can never be negative.
yeah, that is the conclusion that we will get from these three things, right? So from these three cases, we can now say that our mu can take zero value or the positive value. It will not get the negative value. Okay, that's why we said that mu is always greater than or equal to 0. Okay. And whenever we are adding this mu inside the equation, at that time this inequality equation is converting to the equality one. That's why at that time it will be mu I g of x equals to 0, because this is now the equality constant or equality equation, right? So it will be now mu I g I of x equals to 0. Why I? Because this I is for indexing, because there are n amount of inequality constant. That's why there will be I number of mu as well as the I number of g of x. Okay. So any confusion up to now?
Sir, while we are using mu, I mean, this is an extra variable. Right? We are not, it's not like a hard solution that I want to do the hard solution. So mu can be extra solution or
Actually, whenever we are in the condition number 3, we are seeing that we are dealing with the inequality constant. Okay, so it's difficult for us to actually get the inequality equation while solving the problem. That's why in the condition number 4, we are actually converting the inequality constant into the equality constant. And at that time, we have to add another parameter. And this parameter is the slack parameter. Yes, slack parameter. And it will always take positive value or zero value, like this. Okay.
Sir, for example, you gave x1 plus x2 less than or equals to 3.
Yes.
So if it was x1 plus x2 less than or equals to minus 3, in that case, if we take x1 equals to minus 1, x2 equals to minus 1, in that case, mu will be negative.
Okay, very good question. Actually, here always we are thinking about the positive value. Whenever it will be minus, okay, again you have to multiply the minus 1 in both sides. At that time, this symbol will be changed. Whenever this symbol will be changed, this is a different discussion. Okay, but in this discussion, as I already said, that we are only considering about the less than or equal sign. Okay, so always there will be 3 or 5 like this positive value. Okay. Now, in the next slide, the condition number 4 is rewritten here. So this is our condition number 4, that our mu I g I of x will be 0 and mu I will always be greater than or equal to 0. Okay. Now there are two conditions is written over here. Okay. These things will be clear whenever we will solve on numerical problem. Okay. First, read out this thing. Let's say this mu I g I of x should be equal to 0, right? So when the multiplication of these two will be 0, at least one of these should be 0, right? That's why in the first condition, if mu I is 0, g I of x will take this value less than 0. Okay, so this is the inequality constant. Why less than? Because we are following this symbol less than or equal to 0. Okay, so at that time it will be less than. Whenever this mu I is greater than 0, okay, the constant will be 0 or the g of x will be 0. Have you understood this point? Because mu I can take either 0 value or the positive value. Similarly, g of x can take the equal sign or the less than sign, right? So whenever this mu I will be 0, this g of x will be less than 0, and whenever this mu is greater than 0, this g of x will be 0. Okay. And this g of x is 0 means this is the binding condition, means we are at the boundary. Okay. That means whenever, let's say x1 plus x2 less than or equal to 3, we are considering this example. At that time, whenever this x1 and x2 value sums up exactly 3, okay, that will be the equal sign. So that is the boundary, right? 3 is our boundary. Okay. And whenever we are below this value, at that time this is the non-binding case. That's why this is the binding, this is the non-binding case. Then it is said that we have a clear indication of whether the constraints are binding or not. These constraints are binding or not, we will get the clear indication by seeing the value or by observing the value of mu, right? Because if the mu is 0, we will say that our constraint is non-binding because it is than 0. But if mu is higher than 1 or higher than 0, at that time the constant will be binding. Okay, because it will be equal to 0. That thing is written over here. But we have a clear indication of whether the constraints are binding or not. We can say that one by just looking at the values of mu. Okay. Now let's solve one numerical example. At that time we will all the concepts that we have learned here will be clear. So this is the ELD problem with generation constraint. So what is the economic distress for a 3-generator system with PD equals to PD1 plus PD2 plus PD3 equals to 975 megawatt. And the fuel cost function for 3 generators that is given, that is C1, C2 and C3. And so this is alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2. This is alpha 3, beta 3 and gamma 3. These three are the quadratic functions. And the units are obviously dollar per hour. And so these three are our fuel cost functions. Okay. So what will be our objective function? It will be f of x, right? It will be summation of these three. That thing is the C1 plus C2 plus C3. And the target is to minimize this one. That means to minimize the summation of C1 plus C2 plus C3. So this is our objective. And this is the equality constant, right? Look, this is the equality constant. That the summation of Pg1, Pg2 and Pg3 should match the PD of the load unit. That is 975 megawatt given here in this problem. Then there are other sets of constraint. You can see here. This is the limit of Pg1. Okay, so Pg1 should be within 200 and 450 megawatt. Similarly, Pg2 should be within 150 to 350 megawatt, and Pg3 should be within the 100 megawatt to 225 megawatt. Okay, so these are the inequality constraints here. Can anyone say how many inequality constraints are here? 3 or 6? They are actually the 6 inequality constraint, right? How? You can write Pg1, that is greater than or equal to 200, right? Again, this Pg1 should be less than or equal to 450. So for this Pg1 we have 2 inequality constraints. Similarly for Pg2 there will be another 2. For Pg3 there will be another 2, right? So altogether there will be 6 inequality constraints, right? There will be 6 inequality constraints. So, and we know that with the inequality constant we have which variable? Mu or lambda. With the inequality constant we have the mu. So there will be 6 mu, right? Mu 1, mu 2, mu 3, like this up to mu 6. And with the equality constant we have the lambda. There is only one equality constant, so there will be only one lambda, right? And what is f of x? F of x is this. Now, can we formulate the Lagrangian? We can, right? This is the formula for the Lagrangian. It will be f of x plus lambda omega of x plus mu g of x. Okay. So there is only one equality constant, so it will be only one, but there will be 6 terms, right? Additional, like mu1 multiplied by the first inequality constant plus mu2 multiplied by the second one, like this. Okay. Okay. Now look, this is our Lagrangian. Okay. So this term is called the, this is the C1 plus C2 plus C3. So this whole thing is actually the f of x. Okay. This is the objective function. Plus you have to write lambda multiplied by omega of x, right? Or the equality constant. So look, this is the lambda. And how we will write the omega of x for this equality constant? We have to take the right side term in the left side. Right side should be only 0, right? That's why it is, we can write it like this: 970 minus Pg1 minus Pg2 minus Pg3 equals to 0. That's why, look, this is your omega of x. 975 minus Pg1 minus Pg2 minus Pg3. Okay. So this is nothing but this is actually the lambda multiplied by omega of x. Okay. And this is f of x. F of x plus lambda omega of x. Now let's come to the inequality part. Okay. So look, this is the what was the first inequality constant? Let's say here in this problem, this is say as the first one. This is the second one. The same thing. Okay. You can name it as first one. This is the second one. The second. So the first one is the Pg1 less than or equal to 450, right? So what will be the g I of x less than equal to 4? We are actually following this term, right? So how we will convert this expression into this general form, like Pg1 minus 450, right? Less than or equal to g. Now this is the g of x. Have you understood this thing? We have to use this term, and this symbol is less than or equal to. Okay. That's why look, the first one, this is the mu1, and what is the g1 of x? Pg1 minus 450. Okay. Now look at the second one. This is the second one, right? Here will be mu2 multiplied by g2 of x. So what will be the g2 of x? For this you can write Pg1 minus 200 greater than or equals to 0. But in this type of problem we are only following this symbol, right? So now we have to change this sign. How we can do that? In both sides we can multiply the term with minus 1, right? At that time this symbol will be just opposite. So if we multiply it with minus 1, it will be 200 minus Pg1 less than or equal to 0. Okay. So now this is your g2 of x, right? Look, this is mu2 and this is your g2 of x. 200 minus Pg, because you are following this symbol. Okay. In the last class, you may be asked this question, right? Have you got the answer? Whenever we are facing this type of greater than or equal sign, we will just multiply minus 1 and we will change the equal sign. Then we will use this equation. Okay. Then for this Pg2, it is Pg2 less than or equal to 350. That's why it is mu3 Pg2 minus 350. And for this lower limit, mu4 150 minus Pg2. Okay. And for this Pg3, mu5 Pg3 minus 225. And for this mu6 100 minus Pg3. Okay. Have you got the idea? I'm not showing the details of the mu3, mu4, mu5, but these are similar to your the first two, the mu1 and mu2. Okay. So any confusion here? No, right? So this is our Lagrangian. Now, if we think about only this function, this is the unconstrained optimization. Now we will apply the KKT condition from 1 up to 4, right? So what is our first KKT condition? The partial derivative of this L with respect to the PGI, right? With respect to PGI. How many PGIs are there? PG1, PG2, PG3. So we will get 3 sets of equation. The first one will be for PG1. We have to do the partial derivative of L with respect to Pg1, then we will get the first one. If we do the derivative with respect to Pg2, we will get the second equation. This is with respect to the Pg3, right? Now look at the first one. How we can get this Lagrangian? We have to do the partial derivative with respect to the Pg1. Pg1 means what is the Pg1 term? Here, so it will be 5.3. It will be 2 multiplied by 0.004. That will be 0.008 Pg1. Okay. Then look here, this lambda multiplied by this minus Pg1, right? So it will be simply minus lambda. Okay. Then here with the mu1 term, mu1 Pg1. So it will be simply plus mu1. This is mu1 minus Pg1. So it will be minus mu2 equals to 0, right? Then the second equation, if we do the partial derivative of L with respect to the Pg2, we will get this thing. And this is the third equation. I am not going in details of this equation 2 and 3. You will get this thing. Okay. Any confusion up to now? So we have applied the KKT condition 1. Okay. Then the condition number 2. 2 is the partial derivative of this L with respect to our second variable, that is the lambda. Now we will do the partial derivative of this L with respect to the lambda. Okay. Then it will be the condition number 2. What will be the value? Where is the lambda? Only here, right? So it will be simply 950 minus Pg1 minus Pg2 minus Pg3 equals to 0. So we can write it 950 equals to Pg1 plus Pg2 plus Pg3. Okay. condition is nothing but del L over del lambda. So it will be equated with 0. Okay. At that time you will get 975 minus Pg1 minus Pg2 minus Pg3 equals to 0. If you take these three terms at the right hand side, it will be additive term. Okay. So it will be 975 equals to Pg1 plus Pg2 plus Pg3. So this is our condition number 2. Now the condition number 3 is this. Look, this is our condition number 3. So whenever we will do the partial derivative of L with respect to the mu, then we will get this type of thing. So in simpler way, this is actually all the inequality constants. We have to write using only this symbol, right? So how can we write this? Look, this is our inequality constant number 1. That is Pg1 minus 450 less than or equal to 0. This is number 2. It was like this Pg1 minus 200. It was like this. Okay. But if you multiply minus 1 in both sides, it will be 200 minus Pg1 less than or equal to 0. Because always we have to maintain this symbol less than or equal to. Okay. So like this way you can write these 6 equations. So this is your KKT condition 3. Any confusion here? No, right? Now the condition number 4. Okay. So what is the condition number 4? It will be, look, what is the condition number 4? It is mu I multiplied by gi of x equals to 0 when mu I is greater than or equals to 0, right? So there will be again 6 equations, right? So for the first time it will be the mu1 multiplied by what is the g1 of x? This thing, this is our g1 of x. Is equals to 0. And mu1 should be higher than or equal to 0. Similarly, this is the mu2. What is the g2 of x? This equals to 0. And mu2 is greater than or equal to 0. Then mu3 multiplied by this g3 of x equals to 0. mu3 will be higher than or equal to 0. So like this way you will get another 6 equations here for the KKT condition 4. Okay. Any confusion here? So we have applied all 4 KKT conditions from 1 up to 4. Okay. So how in these 4 conditions, how many unknown variables are there? Pg1, Pg2, Pg3 and lambda. There are 4 and there are 6 mu, right? So altogether there are 10 unknown variables. Okay. And to solve the 10 unknown variables, we need at least 10 equations, right? We have more than 10 equations. That's not the problem. But to solve 10 variables is very much difficult for us, right? So what we can do, now we will consider the first case. Okay. So in the first case, okay, we will see that all the mu, we will consider that all the mu values are equal to 0. Okay. Now let's think about the previous example that I gave while discussing the condition number 4. This is your condition. Okay. Now you converted this inequality constant into the equality one. How? By adding a new term with this, right? Now I said that in one of the case you got x1 as 3 and let's say x2 as 0. So it is 3 plus 0 equals to 3. That is equal to this 3, right? So this condition is violating or satisfied. This is satisfied. But for this case, what will be the value of mu? Mu will be 0, right? That means whenever mu is 0, that means automatically that inequality constant is transferred to the equality condition, right? So now in this case, we are assuming that all mu values are actually 0, right? So if all the mu values are 0, that means all the inequality constant are now transferred into the equality one, right? Now if we assume all mu values equal to 0, what are the advantages? The advantage is that this mu will be cancelled out, right? So we will have only 4 unknown variables. Pg1, Pg2, Pg3 and lambda. Okay. So this is the case number 1. Look, we have assumed all the mu values at the equal to 0. Okay. There is another meaning of this thing, that mu equals to 0 means the Pg1, Pg2 and the Pg3, the final answer of the Pg1, Pg2 that all the new values are 0, that means all these values Pg1 and Pg2 and Pg3 are within the limit. Okay. So considering this, we will solve. If all the Pg1, Pg2 and Pg3 are within the limit, then that's okay. That will be our final solution. But if any of them violates, at that time we will do the treatment of that term. Okay, that is the idea here. So if all mu values are 0, so we will get this type of equations. Okay, from where? From this KKT condition 1 and 2. Look, this mu will be cancelled. Okay, then we will this equals to 0, this equals to 0, this equals to 0, and from KKT condition 2 it will be 975 equals to Pg1 plus Pg2 plus Pg3. Okay. Now there are 4 equations, 4 unknown variables, right? So you can form the matrix by using the calculator. You can find the Pg1, Pg2, and Pg3 and that, right? Let's say these are the values of Pg1, Pg2, Pg3, and level. Okay. Now you have to look at the limit. Okay. Look for the Pg1. What was the upper limit for Pg1? It was 450 megawatt. But you are getting 482.89. So it is violating the upper limit Pg1, right? And for Pg2, it is 305. Is it within the limit? Yes, it is within the limit for Pg2, right? Then for Pg3, it is 186. Is it within the limit? Yes, it is within the limit, right? So Pg2 and Pg3 are okay, but Pg1 is violating the upper limit only, right? Because look, this Pg1 for any particular generating unit, let's say for Pg1, is it possible that this Pg1 is both violating the upper limit and lower limit at the same time? It is not possible, right? Either it will be within the limit, or it will violate the upper limit, or it will violate the lower limit, right? Let's say it is 482. That means it is violating the upper limit, that is 450. If it was, let's say, 50 megawatt and the lower limit was 100 megawatt, that means it is violating the lower limit. But if the value is in between 100 to 450, then it is within the limit. Okay. And this is the lambda. Lambda is the incremental cost. Now this set is not a valid solution because the Pg1 is greater than Pg1 max. Okay. Now in the case number 2, we will do the treatment of this Pg1. Okay. How? Look, in case number 2, Pg1 should be bound at its upper limit. Okay. So that was the ELD problem. ELD problem gives us the set of solution that will actually minimize the fuel cost. Okay. From this result, you get a clear indication that the fuel cost of this Pg1 is actually less. That's why it is generating more power. Okay. But there is the limit. You can break this limit. So what you can do? You can take the maximum power from Pg1, okay, then you can redistribute the rest of the power into Pg2 and Pg3. That will be a solution. Okay. That's why in case number 2, we are saying that Pg1 should be bound at its upper limit. So Pg1 is now fixed. It is 450 megawatt. Okay. Pg2 and Pg3 are within their upper and or lower limits. Also Pg1 is within its lower limit. Okay. So as the Pg2 and Pg3 are within their lower and upper limits, as well as the Pg1 is within the lower limit, right? That means these variables will be 0, but as Pg1 violated the upper limit, so the slack variable that was associated with that part, that is the mu1, will not be now equal to 0. It will take a value that will be greater than 0. Okay, let us understand this part. Only this thing is violated. This Pg1 is now greater than 450, right? So the associated slack variable is mu1. Now we will treat that this mu1 is greater than 0. Other mu are 0 as well. Okay, because here no violation is there. So the assumption that we took in the case number 1, that are okay for mu2 up to mu6. Okay, but only mu1 is not the correct. That's why. But we take mu1 is greater than 0, but the other Now we have to again formulate the Lagrangian, the same form Lagrangian. We have just copied and pasted it here. Now again apply the condition. The first condition will give you this thing. This is the first condition. The same thing. Okay? The same condition for condition 1, 2 and 3. We have just copied and pasted from here. The same. Okay? There is only change in condition number 4. Okay, what is the change? For the first condition, we know that our mu1 is now this thing. Okay? And why we didn't write the other part that was mu1 multiplied by Pg1 minus 450. Why didn't write this thing? Because this term is 0, right? This is 0 because now Pg1 we have set it to 450. So 450 minus 450 will be 0. That's why we didn't write this thing. Only this is thing and the other equations are kept as it was.
Sir, when we write mu1 greater than 0.
Yeah, actually this is the mu1 greater than 0, the same thing, okay? Because it is not equal to 0. We have found just that thing, okay? So you are telling that, sir, we can directly write mu1 greater than 0. Why we are writing equal sign, right? Okay, you can omit this equal sign, but we know that this will be obviously greater than 0, okay? Now again solve the problem. So now look, your mu2, mu3, mu4, mu5, mu6 are 0, right? That means look at this thing. Here there is only mu1, but mu2, mu3, mu4, mu5, mu6 are 0. That's why there are no smart variables from mu2 up to mu6. Okay, there is only mu1. Now what are the unknown variables now? This lambda, this Pg2, Pg3 and this V1, this 4. But this Pg1 is known to you because you have set Pg1 as 450 megawatt. So this solution is known to you. Now the new unknown variables are mu1, lambda, Pg2 and Pg3. Okay. Now look, these are our equations. Okay. So Pg1 is 450. So this is the unknown variable. This is the unknown variable. This and this. 4 unknown variables. How many equations are there? 4, right? So we can easily solve the problems. After solving,
In case 1 we have also got the value of Pg2 and 3. Those are also within the range.
yeah, those are within the limit. But whenever you are changing the values of Pg1, so let's say you got the solution of Pg1 as 482. That was violating the upper limit. That's why you set it to the maximum limit, that is 450 megawatt. So the rest of the 32 megawatt you should be distributed to inside the Pg2 and Pg3, right? Otherwise, the equality constant, that is the summation of Pg1, Pg2 and Pg3 should match the PD. That things will not be satisfied. Okay, that's why for this case too, we will get the new solution for Pg2 and Pg3. That's why these two are still unknown parameters. Okay, so from these 4 equations, we can get Pg2, Pg3, lambda and mu1. Look, mu1 is not 0, it is 0.5. That is the positive value. Okay, greater than 0. And look at the Pg2, it is within the limit. Also Pg3 is within the limit. And Pg1 is 450 megawatt. That was the maximum limit. Okay, now add this 3, 450, this 55, 325 and 200. You will get 975 megawatt. Exactly, that is matching with your loading, right? So your equality constant is satisfied. Also your inequality constant or the generation limits are also satisfied, right? Have you got the idea? So this is your final set of solutions. That will Pg1 will be 450 megawatt, Pg2 is 325 megawatt, Pg3 200 megawatt. What is your lambda? 9.4. The unit is dollar per megawatt hour. This is the incremental cost. And this is your slab variable V1. It is 0.5. Okay. So as none of the constants are violated, so this is the optimal solution. Okay. Have you got the idea how you will solve this type of problem? That is dealing with the inequality constant.
So if multiple constants are violated, then you will have to solve 5 or 6 equations.
Yeah, okay. So very good question. Actually, the thing we have already discussed here. Okay, good. For just think about one generating unit. That's a PG1. For the PG1, the violation will be either in the upper limit or lower limit, not at the center, the both. Okay. Similarly, for PG2, the violation will be either in the upper limit or lower limit. Same for the PG3, it will be either upper limit or lower limit. Okay. That means, let's say there was the violation also. There was the violation also. Okay. Let's say it is what was the limit of PG2? From 150 to 350, right? Let's say you got this value as 375. Okay. Now it is violating the upper limit. So, and this is 482. So you have to set PG1 as 450 megawatt and PG2 at 350 megawatt, right? The maximum value. And let's say also this is violating. Let's say you are getting this as let's say 50. Okay. Let's say you are getting this as 50 megawatt, but the lower limit is 100 megawatt for this PG3. So then you have to set this PG3 as 100 megawatt. So now there is no option in your hand. So this will be your final solution. If after adding, if you are not getting the PD that is 975 megawatt, if you are not getting this value, then you will say that this is an invalid solution. Or for this problem there is no optimal solution. That is the case. So this type of scenario may come that you are not getting an optimal solution for that type of problem. Okay. It may occur, right? Let's say you are an engineer and I have no knowledge about engineering. So I want something from you. I am telling you that okay, you have to do this thing. And you are saying that no, this is not possible. Okay, so there may have the scenario that the optimal solution is not coming from the problem statement. So you have to redefine the problem statement to get the optimal solution. Okay, have you got your answer? So this was the numerical problem regarding the inequality constraint. Then the next type is the ELD with transmission losses. Okay, this is our last topic or the last time. Because up to now we haven't considered the transmission losses. In the first type, we discussed the unconstrained minimization problem. Then in the next type, constraint minimization but only with equality constraint. Then the next type, the constraint optimization problem with inequality constraint. Now in the last type, we will solve the ELD problem with transmission loss. Okay. So for this thing, I will prepare a recorded lecture. I will supply it to you. Okay. You can watch it in your convenient time because you have maybe 3 days practice before my mid exam, right? So at that time you can watch that video and you can. So I think we can conclude here.